Oh, yeah, you are correct. Yes, lab 2 is just a continuation. Okay, good morning, everyone. So, usual updates, homework assignment is due tonight, and then you're gonna do lab number 2 next week. And so someone came up and they correctly reminded me that there is no pre-lab number 2, so you don't have to worry about a pre-lab for next week. In lab number 2, what you're gonna do, it's gonna be a continuation of the first lab. In the first lab, you've done some rough measurements of the period of a pendulum as a function of the angle of release. And hopefully what you saw is that there was basically no change in the period as predicted by the derivation that we did at the start of term. What you're going to do next week is you're going to repeat those measurements, but you're going to make some more precision measurements of the period as a function of angle, and hopefully uncover possibly some unexpected behavior. Okay, now before I recap what we talked about last time, here are the distribution of quiz grades. So the average was 64%, which is pretty typical year after year. That's sort of where it lands. Actually, this is maybe a little bit higher than normal, so that's good. And then 22% of the class got 80% or better. Okay, and so those are the statistics. There's a big peak sort of in the 70 to 80 range, and then tails off on the other side of that. Okay, and the stuff that we've been talking about is Gauss's law. And for Gauss's law, what we had was 2 different ways of calculating electrical flux for a closed surface. One was to evaluate this integral of the E dot dA, and then the other was to find the total charge enclosed by that surface and then divide by the constant epsilon naught. Those 2 have to be equal to each other. Now, in general, evaluating that integral is difficult, but we came up with some strategies that make this calculation a little bit easier. And the strategies involve picking a surface that surrounds our charge distribution, and choosing that surface so that the electric field is either going to be perpendicular or parallel to different parts of that surface. When the electric field is perpendicular, then we get the maximum flux, and E dot dA can just be written as E times A, gets rid of the dot product. When the electric field is parallel to the surface, then it contributes no flux, and that contribution just vanishes. And so we try to make those choices to get rid of the vector part of this expression. And then we try to choose our surface so that the electric field is going to be constant over the parts that contribute non-zero flux. And if we can do that, we can pull the electric field outside the integral. You can always take constants outside the integral. And then that simplified things. We did an example at the end of our, I guess, Monday class, and it was a charge sheet. So the sheet has a uniform charge per unit area, which we denoted by sigma. And then what we calculated using Gauss's law is that the electric field was equal to sigma over 2 epsilon naught. And that's kind of an interesting result, because notice that it doesn't depend on how far away you are from this charge sheet. I could be very close to it, or it could be very far away, and the strength of the electric field doesn't change. So if you think now back to a point charge, as you move away, the electric field drops off as 1 over r squared. If you had a line of charge, a 2D charge a 1D charge distribution, then the electric field was lambda over 2 pi epsilon naught r. So it falls off as 1 over r instead of 1 over r squared. Now, when we have a 2D sheet of charge, the electric field doesn't depend on r. Okay. So the first thing I want to do is I want to do kind of an application of this sheet of charge. So let's do a sheet of uniform charge, and then we'll do an application. So in fact, what we're gonna do is we're gonna take two sheets of charge and we're gonna place them parallel to one another, one above the other. Our application is going to be to make a parallel plate capacitor. So we're gonna consider two parallel sheets of charge with equal but opposite charge per unit area. And we'll call that charge per unit area sigma. All right, and so what it would look like is maybe we have one sheet of charge is over here and it's got a bunch of positive charge. I'm gonna look at a side view because it's easier to draw. And so this is charge per unit area plus sigma. Okay, and so here's our side view. And then what we'll do is we'll draw a parallel sheet just below it, but we'll give it the same charge per unit area, except all the charges will be negative. So we'll put that one over here. And so, so there's all our negative charges. And so this has charge per unit area of minus sigma. Okay, so what I'm going to do is I'm going to draw the electric fields due to these sheets of charges. And the way we're going to think about it is, we'll first imagine that only the positive sheet is in place, and we'll draw what its electric field is. And then we'll imagine that only the negative sheet is in place, and we'll draw its electric field. And then we'll realize that the net result is the sum of those two. So that's called superposition. So we can separately think of the electric fields due to the positive and negative sheets individually, and then add them up in the end. And so let's just write down that strategy first. So we will first draw the electric field due, this thing's slow, due to the positive sheet. Then draw the electric field due to the negative sheet. The net electric field is the sum of the two. Okay, and let's just remember, we wrote it down above, but the electric field due to a sheet of charge was sigma, the charge per unit area divided by some constants, 2 times epsilon naught. Okay, and we also know that the electric field will be perpendicular to these sheets. So let's start with the positive one. We know that electric fields point away from positive charge. So if I'm above the charge sheet, the electric field will be pointing up. And if I'm below it, it will point down, right? Always away from the positive charge. Okay. Now, the other thing that we have to keep in mind is that if I move farther away from the positive sheet, the electric field strength doesn't change, right? There's nothing in here that depends on how far away from the sheet I am. So if I move further away, the electric field doesn't change. It still looks exactly the same due to this positively charged sheet. All right, and so that's step one. We just drew the electric field only due to the red positive sheet. And next, what we're going to do is we're going to add the electric field that's due to the blue negative sheet. Everything's going to be exactly the same, except that electric fields point towards negative charges instead of away from them. So everything looks the same. We just have to make sure that the electric fields point towards the negative charge when we're thinking about, well, the electric field due to the negative sheet. And so it looks something like this. And so there it is. So when you look at a picture like that, what's the electric field going to be above the red positive sheet? What's the net electric field going to be? 0. It's going to exactly cancel because we have two contributions to the electric field. The sheets have exactly the same charge per unit area, just different in sign. So they produce the exact same magnitude of electric fields. And so if they're in opposite direction, they cancel. Likewise, below the negative sheets, the two contributions are in exactly the opposite direction. And so they cancel exactly. So above and below the parallel sheets, E net is equal to 0 because the two contributions are equal in magnitude and opposite in direction. Okay, that's fair enough. But then the only place where that doesn't apply is if we look between the two sheets. And there, again, we still do have contributions that are equal in magnitude. They're in the same direction in this case. And so there's not going to be a cancellation. Instead, they will add up. And so we'll have two contributions of sigma over 2 epsilon naught. And when we add them up, they just double. And so the net electric field between the sheets will be sigma divided by epsilon naught. Okay, so on the other hand, the two contributions to E net add between the sheets such that we get E net has a magnitude of sigma over epsilon naught between the sheets. All right, and what's nice about this is that these parallel sheets give us a way of creating a perfectly uniform electric field that exists in a confined region of space. It exists only between the two sheets, and the electric field is 0 everywhere else. So that's very useful to be able to make these uniform electric fields. A lot of the problems that we've done so far involve something in a uniform electric field. And so here's an actual practical way of creating that type of environment. We won't discuss it now, but in a couple of chapters later on, we will return to these parallel sheets, to capacitors, and we'll find that they're useful for storing charge. So for example, your phones, you all have like a camera with a flash on it, and to make the flash very bright requires a lot of charge to be deposited through whatever the light source, the lamp or LED or whatever it is in your phone. You need to pass that charge through your light very quickly in a short time. And you can't do that with just a little 5-volt battery that's inside your phone. So what they do is they typically will charge a large capacitor, store a lot of charge on these sheets, and then have all that charge flow through your flash in a short time. So a very high current, a high rate of charge flow. And so then you take all the charge off your sheets, put it through your light, and then you get this brief bright burst that you can illuminate your surroundings while you take this picture, and then you charge your capacitor back up. Okay, so, whoops, sorry. The parallel sheets. Or the capacitor gives us a way to create a uniform electric field between the plates with E equal to 0 everywhere else. Okay, and so let me just draw that. We'll draw this one more time. So we'll take our positive sheet, and below it, we'll put our negative sheet. And then the electric field is going to be 0 over here, 0 below the plates, and it'll be non-zero between the plates, and it'll have a magnitude of sigma over epsilon naught. In this case, well, let me just draw the magnitude out. Won't worry about the direction. The direction is shown by the arrows there. Okay, good. So there's a real application, and this sort of thing is done all of the time. The other thing you can do with these uniform electric fields is you can use them to accelerate charges. So if I put a charge between these plates, it'll be a force of Q times whatever the electric field is, and therefore it'll accelerate. And so you can give your charges some speed, maybe if you're going to use them in some kind of particle accelerator experiment or something like that. Okay, good. Any questions about this example? Yeah.
Just above the positive plane, could be with electric field be a little bit like stronger outwards, or vice versa beneath the
No. So for an ideal infinite sheets, the electric field will be exactly 0 just above and just below the sheets. So there's an exact cancellation. Yeah. In practice, we could never make infinite sheets, so they'll be finite in size. And so what you end up getting is these fringing fields, but they'll be very weak on the other side. They won't be a little bit stronger, they'll be very weak. Yeah. Perfect. Okay, good. So what I want to do is I want to finish off with one more example of using Gauss's law. Before we get into it, what I want to do is I want to emphasize that there's really only 3 scenarios where Gauss's law is easy to use to find electric fields of different charge distributions. And we've done 2 of them already. The reason why there's only a few scenarios where it works well is because we require this geometry where we find surfaces that are either parallel or perpendicular to the electric field. And that's only easy to do in some limited cases. So Gauss's law is easy to apply in 3 scenarios. And so if you can master these 3 scenarios in which you can use Gauss's law, then you'll be prepared to answer essentially any type of question I could ask you to do. So one is a point charge or a spherical distribution. of charge. And so by a spherical distribution of charge, what I might mean is maybe you have like some kind of sphere that has some uniform charge throughout its entire volume. So that's a spherical distribution of charge. Whenever you have a spherical distribution of charge, it'll make electric fields that point radially away from the center of the sphere. So here, the electric field will be in the radial direction. And what we're going to do to match that symmetry is, so maybe I could draw that. Let's draw a spherical distribution of charge. So it's something like this, and the electric field due to this spherical distribution of charge will point in the radial direction. I'll draw it just in this plane, but of course there are electric field lines out coming towards us and pointing into the screen as well. And so what we're going to do is we're going to select a spherical Gaussian surface. Such that E is constant and perpendicular at the surface. Okay, and so our Gaussian surface will be this blue thing. I don't love that. It's supposed to be, I want the centers of my two spheres to coincide. And so let's draw something. Maybe that's a little bit better. Okay. And so we'll label this as our Gaussian surface. So if I was to choose my dA vectors, remember, they're always going to be perpendicular to the surface and they're going to point outwards. And so no matter where I am on that blue spherical surface, the dA and the electric field E will always be parallel. And if I was to evaluate something like this integral, I would say, okay, E and dA are parallel, the dot product goes away. I won't write down all of the little details because we've done this already. And then I would say, okay, the electric field is constant on the blue surface because the blue surface is always the same distance from the charge. And so if the electric field is constant, I take it outside. And this integral of dA just gives me the area of the sphere. So a sphere, which the area of a sphere is 4 pi r squared, where r is the radius of our blue spherical surface. So that's it. So whenever you have some kind of spherical charge distribution, pick a spherical Gaussian surface, and your integral will be given by this type of expression. Then, in order to finish off Gauss's law, all you would do is say that that was equal to Q enclosed divided by epsilon naught, and then you can solve for E. So we did this for a point charge. It's the first example we did. All right. So the second scenario where Gauss's law works is when you have a flat distribution of charge. And so that's the example we did last time, the sheet of charge. And so we could draw our sheets. And we'll go through this one quickly because we just did it last time. But there's our sheet of charge, and you know, it keeps going. I've just drawn a section of it. So what we're going to find is that the electric field will be perpendicular to this sheet of charge. So below, it'll be pointing downwards, So here, I'm gonna get rid of these arrows because they confuse, looks a little confusing. So here are our electric field lines. Something like this. Okay. Now what we did to choose our surface is we could choose a surface of any shape. We just want it to have flat tops and bottoms. Okay, so what we could say is E is perpendicular to our sheet. And what we're going to do is we're going to select a Gaussian surface with flat top and bottom. Okay, so we could draw some kind of surface that looks like this. And so there it is. And then it goes underneath and it also looks the same kind of shape. And so here is our flat top. And so let me call this a top. And below here, we would have our bottom. A bottom is equal to a top. Okay, so the cross-sectional shape could be anything, but we want top and bottom to be flat and have equal area. If we do that, then we can say, well, this integral of E dot dA, it's going to involve the top area, the bottom area, and the side area of our surface. But the side is going to have a normal vector that's perpendicular to the electric field. And so it's not going to contribute any flux. There's no flux through the side surface. And so this ends up being the 2 times the integral of E dot dA for the, well, here, let's do it this way. Let's do E dot dA of the top plus E dot dA of the bottom. But because we chose our top and bottom surfaces to be the same shape and same distance from the charged sheet, we could just say that that's 2 times the integral of the top surface E dot dA. But then we say, okay, the top surface is exactly perpendicular to the electric field. So we get maximum flux. We can ignore the dot product. Yeah, go ahead.
When you say Gaussian surface,
Yeah.
is that distinct from any regular surface? And what exactly does that mean?
It's any surface that you want. It could be completely imaginary, or it could be like some physical surface where you want to know the actual flux to a physical surface. But we're just choosing. So the Gaussian surfaces are these blue ones. And so I'm just choosing a convenient surface, imaginary, that is at a position where I want to know what is the electric field at the top of this Gaussian surface, right? So if I said, I want to know what the electric field is at distance d above this charged sheet, I'm just going to place my top surface at distance d above that sheet. And that's where we're going to find the value of the electric field.
So it's a convenient.
Yeah, exactly. Okay, now our top surface is flat, so every piece of that surface is the same distance away from the charged sheet. And so the electric field would be constant. And so this would be 2E times the integral of the top piece, dA. But that's just 2E times the area of the top surface. And so if you're ever dealing with a Gauss's law problem that involves a sheet of charge, this is how you would set it up. So those are 2 of the 3 possible cases. And there's only one more. Can anyone guess like what we have? Spherical symmetry, we have like a planar symmetry. What other common shape might we encounter? Cylinder. So that's the only one we haven't done. Okay. And so that's what I want to do with the remaining 20 minutes that we have here. So 3, is a cylindrical distribution of charge. Okay, so this could either be like a line of charge that we've already done, or it might be like a rod that has some like radius to it. And so let's think about that. Let's draw a charge rod where I'm going to assume that the charge is uniform throughout the volume of this rod. And so this is all charged up. Okay. So we assume that the rod is charged uniformly throughout its volume. Okay. When we had a line of charge that was uniformly charged, we said it has a linear charge density of lambda. When we had a sheet of charge that was uniformly charged, we said it had charge per unit area sigma. Here we have some volume with a uniform charge density. We're going to call that charge density rho. Okay, so this is rho is Q divided by whatever the volume is. All right. So what we have to think about is if we have this kind of shape, what's the direction of the electric field going to be? Is it going to be like slanted to kind of the left or the right? Yeah.
I think it would be just like always perpendicular to like the circle.
Yeah, exactly. Always perpendicular. Yeah. So yeah, that's right. So it's going to be another radial electric field, but it's radial in a cylindrical sense. And so we would have an electric field that's always going to be pointing, because I drew them positive, will be pointing radially out. Oops, I can do that one a bit better. So let's do a side view so that we could see this. So in a side view, we would see the circular cross section of our cylinder, and our electric field would be pointing in this radial way. So this is E, and this is E. Okay, so what we're going to try to do is we're going to try to pick a Gaussian surface that matches the symmetry or geometry of our cylinder. And so what do you think we should choose for our surface? We have a cylindrical rod, so what should the shape of our surface be? A bigger cylinder or a smaller cylinder, like any kind of cylindrical shape where we have a common axis between the rod and our Gaussian surface. Okay, so what we're going to do is we're going to select a cylindrical Gaussian surface. And so I'll draw that for you, and then we'll talk about what the reasons for this. So my Gaussian surface might look something like this. And so I'll give it some radius R, and we'll give it some length L. And then what we have to recognize is that our cylindrical surface has three parts. It has two end pieces, and then it has the curved surface. And so, okay, and then over here, it would look like this. Something like this. Here's our radius R. What would the flux through either the left or right-hand side piece be? How many electric field lines pass through one of the side surfaces? the electric field is exactly parallel to the side surface, so none of them actually pass through that piece of surface, and so they don't contribute any electrical flux. So our cylindrical surface has two side areas and a curved surface. So what we could say is the integral that we have to evaluate is this E dot dA. And so it's going to be like the integral of E dot dA for, say, the left side surface plus the integral of E dot dA for the right side surface, and then it's plus the integral of E dot dA for our curved surface. But because the electric field is perpendicular to the normal vector of the two side surfaces, the dot product is going to vanish. And so these are going to contribute 0. This is going to contribute 0. And we're left only with the side surface. So in this case, the flux that we're trying to calculate is just E dot dA. Sorry, did I say side surface? We're only left with the curved surface. Okay. Yeah.
Why don't we electric field line going
So what I'm thinking about is a very long rod. Okay, so this is a, let's say, very long. So you're right. If it was a short rod, then near the ends we would get electric field lines that wouldn't be perpendicular. But let's imagine this is very, very long. Okay, so then if I look at that curved surface, the dot product is going to be E dot dA is going to be E dA cosine of 0. Cosine of 0 is 1. The dot product goes away. The other thing we'll look at in this picture is that blue surface is always the same distance away from our charge distribution. So E will be a constant. And so this is going to be curved surface. First step, the dot product goes away. Second step, the electric field comes outside. And we just have to integrate over the area of our curved surface. And so our flux is going to be E times the area of the curved surface. What's the area of the curved part of a cylinder? A cylinder of radius R and length L. Well, you could imagine taking that cylinder and then cutting it along the length and then unwrapping it. One edge, so when you unwrap it, look at a rectangle. The length of one edge of that rectangle will be the length of the cylinder, and then the other edge will be the circumference, 2 pi r. And so the area is going to be 2 pi r times L. And that's it. If you can get yourself comfortable with dealing with the integral of E dot dA for spherical surfaces, for geometries with flat charge distributions, and for the cylindrical geometries, that's the only ones that you're going to encounter. So did you have a question? No. Okay. All right. So we have 10 minutes left. So let's see if we can actually solve this problem for our cylindrical surface. And so I'll restate the problem. So consider a long, uniformly charged rod of radius, let's say capital R, and charge density rho. So what we need to do is we need to find the electric field. We'll do two parts. Part A is a distance r, say greater than capital R, away from the rod. Let's say from the axis of the rod, away from the axis of the rod. And part B is going to be, part B will be a distance r that's inside the cylinder somewhere. A distance r that's less than capital R from the axis of the rod. Okay, so this is first part A is outside the rod and part B is inside the rod. Okay, A. I'll draw the picture again, but we've done a lot of the work already. So here's our charged rod. And here's our Gaussian surface. This is going to be radius little r, and this is going to be radius big R. The length of our surface is L, like so. All right, so we would apply Gauss's law, which just says that this integral of E dot dA is going to be Q enclosed over epsilon naught. But we've already done the integral, right? In fact, the result is probably right there. Everything we did would just be exactly the same. We would say there's two side surfaces, don't contribute any flux. We only think about the curved surface. And so the result is E times the area of that curved surface. So this integral is going to be E times the circumference times the length. And so really what we're left to do is to figure out Q enclosed. So if we know that we have a charge per unit volume rho, then we just have to find the volume of the rod that's inside of our closed surface. So Q enclosed is going to be rho, which is the charge per unit volume of our rod times the volume of the section of rod inside our blue Gaussian surface. Right, so if we know the volume of the rod that's inside our surface, and we know the charge per unit volume of the rod, the product of those two gives us the charge. So we can, the relevant volume is this one. I'll try to shade it. So this is the relevant volume. So what's the volume of that red shaded section of our rod? So it's a cylinder of length L. So the cylinder has length L and has a cross-sectional area of pi r squared. And so the volume inside our charged surface, inside our Gaussian surface is pi r squared times L. Okay, and so then Q enclosed is, sorry, I made a mistake. Does anyone see, what mistake did I make? Does anyone see it? Yeah. That's right. So I want that red volume, and we said the rod, that's exactly right. We said the rod has a radius of capital R. So there we go. Good. Perfect. Okay, so Q enclosed is rho pi r squared L. So now we know we've evaluated the integral, we've evaluated Q enclosed, we can equate the left and right-hand sides of Gauss's law, which says that E 2 pi r times L is the integral, is Q enclosed, which is rho pi big R squared L divided by epsilon naught. So this is Gauss's law. All right, and so let's see, there's some cancellations. L is on both sides. That's nice because choosing the length of our blue Gaussian surface was arbitrary. I could have chosen a shorter one or a longer one. It wouldn't make any difference because those factors of L are just going to cancel. There's also factors of pi that cancel, and then we could just solve for our electric field. And so E is equal to, we just have to divide by 2r, right? It's rho r squared 2 epsilon naught r. This is outside the rod for r greater than capital R. Let me just check that we did that right. I think it's probably right. Yep, looks like it. Okay, good. Let's see if we can quickly do inside the rod. So for inside the rod, what we'll have to do is we'll have to draw our rod here. And so it's charged up. I won't draw the charges because it just clutters the picture. But now I'm going to place my cylindrical Gaussian surface inside here. We'll still give the Gaussian surface radius little r and length L, and we'll still call the rod radius big R. Okay. One of the beautiful things about this is that we've already done the integral. Nothing changes about the integral of E dot dA. It's still true that the side pieces contribute nothing. The curved surface does contribute something, but it still is just going to be E times the area of that curved surface. So just like in part A, this integral is going to be exactly the same thing. The only difference is we've made little r smaller, but the calculation doesn't change at all. What does change is Q enclosed. So now Q enclosed is equal to rho times the blue shaded volume. And so I'll shade it. So it's inside here. Our surface is small, so there's less charge inside of it. And so the blue shaded volume is smaller than the red shaded volume. The blue shaded volume, it's still a cylinder. So this time it's going to be pi. This time it is little r squared because our blue surface is radius little r times L. And so Q enclosed is equal to rho pi little r squared times L. And the last thing we have to do is set the left-hand and right-hand sides of Gauss's law equal to each other. So the integral is the left-hand side. So Gauss's law requires, let's see, the integral gives us E 2 pi r L, and Q enclosed over epsilon naught gives us rho pi little r squared L divided by epsilon naught. Some of those same things cancel. The L's cancel, the pi's cancel, And now there's one more cancellation, 1 factor of little r cancels. And so to solve for E, we just have to divide by the 2 now. And so E is equal to rho. Let's see what's left over, R divided by 2 epsilon naught. And so this is for a radius that's less than big R. And so this is for points. Whoops. This is for points inside the rod. Okay, and so let's see, where's our other results? There we go. So outside the rod and inside the rod, there's one point where these things should be equal. At what point should these two expressions for the electric field be equal? Yeah.
When their volumes equal?
Yeah, when little r is equal to big R. So if we take little r and make it big R, that top equation is going to be rho big R divided by 2 epsilon naught. The bottom equation would be rho times big R divided by 2 epsilon naught. And so they're equal. So there's some self-consistency between these two. All right, good. Thanks very much. Have a good weekend, and we'll see you on Monday.